Okay, so we're getting ready for our next talk, which going to be, first up will be John Ackerman. And the update is on the Tangerine SDR hardware update. We got 3 speakers in turn. John Ackerman and N8UR will be first. Next up will be Tom McDermott, N5EG, and then last but not least is Scotty Cowling, WA2DFI.
Hi, this is a report on the design of the clock module for the Tangerine SDR. Tangerine SDR requires a couple of different clock frequencies. The most important one is probably the 122.88 megahertz that drives the RF modules, but there's also a pulse per second along with timestamps that are used for data tagging, and we'd like to have a 10 megahertz general purpose reference signal available. Those signals will all be generated by a GPS disciplined oscillator. In addition, the GPS module will allow us to generate a measurement called a total electron count, which is something that the science community would like. So we'll make that data available to the data engine as well. The GPS-DO specifications are a little bit hard to pin down because the science applications are so broad, but after talking with the teams, I think that the following specs will more than meet the requirements for all the science experiments that are currently contemplated for the Tangerine SDR. And that's a frequency accuracy of better than 1 part in 10 to the 12th, or a part per trillion, a frequency stability in the short term of better than 1 part in 10 to the 9th, or 1 part per billion at any tau or averaging interval from 1 second or greater. The absolute PPS time accuracy will be within 100 nanoseconds of UTC as realized by the US Naval Observatory, and the jitter on the PPS signal will be less than 10 nanoseconds. Because this is an RF application, phase noise of the 122.88 megahertz is important, and our target there is better than minus 80 dBc at 100 hertz offset, and better than minus 150 dBc at 100 kilohertz offset. As I mentioned in my previous presentation, a GPS-DO is really a way to get the best of both worlds of using the better short-term stability of a crystal oscillator and the long-term accuracy and stability of the GPS constellation. The magic is to use a PLL, a phase lock loop, with a time constant that allows the crystal oscillator to dominate in the short term, filtering out the noise of the GPS signal, which takes over in the long term. This plot, which I shamelessly stole from the SRS company's website, shows a GPS-DO model for a little bit different environment. They're using a rubidium frequency standard, which is much better in terms of short-term performance than the crystal oscillators we're using. But the plot clearly shows how this all works. Here we have the GPS pulse per second signal at the black line, and you can see it's quite bad at short term. It keeps getting better and better and better. The red line is the rubidium standards raw output, and you see it's quite good, and it stays quite good for a long time, but ultimately it starts to become worse than GPS out here near the right of the plot. With a properly designed phase lock loop, we'll get this blue line where we get the short-term performance, but then we transition to the long-term of GPS. Now, we lose a little bit in this transition interval, but that still isn't bad, and it gives us a single source that has the best of the short-term and the long-term performance. And that's what we're trying to accomplish in the Tangerine SDR clock module. So to take advantage of the performance improvements that we get by using the dual frequency receiver, we can look at the previous chart and sort of redesign it. Since our noise after dual frequency plus sawtooth correction is down around 5 and 10 to the minus 10th. That's actually better than our short-term spec. We don't need a long time constant. We can use just a few seconds. And that allows us to use an oscillator that doesn't have long-term performance that's as good. And that means that's a cheaper, lower cost oscillator. And we can spend that money instead on the more expensive GPS module. So we may not save money overall, but we're transitioning where we're spending the money to be able to get other features. This Allen deviation plot kind of shows the tail. The green trace is the performance of a crystal oscillator that's very similar to the one that we'll be using. And you can see that its best performance occurs at around 1 second right in here, but it starts to go up fairly rapidly because of temperature and aging and other factors. This blue line is a traditional GPS, and we can see that the point where they cross over is out here at about 25 seconds, and the Allen deviation at that point is about 2 × 10⁻⁹. That's not quite as good as we would like our system to be. However, if we switch over and use the ZF9T PPS, which is the magenta line, now the intercept point is at about 2.5 seconds, and the worst case Allen deviation is about 2 × 10⁻⁻10. So we've picked up an order of magnitude in performance, and now we can generate a signal that is actually quite a bit better than the specification, which is a good thing because we'll never quite achieve this absolute crossover in practice. The noise hump at the transition will probably be just a little bit higher. So this design should let us meet our design spec using a direct control of the 122.88 megahertz TCXO. And that means we don't need a 10 megahertz oscillator in the mix either, which is another cost that we can reduce. So the key design points of the GPS-DO are, again, to use the low PPS noise to allow a short time constant. We'll phase lock the 122.88 TCXO directly to GPS. There won't be a 10 megahertz crystal oscillator. However, we'll make a 10 megahertz output available by synthesizing it in the FPGA. And speaking of that, the FPGA will serve as both the connection matrix and the processor for the clock module. Pretty much everything goes through it. And the reason for that is to allow us to reconfigure the system quite easily without having to move a lot of hardware around. The board will allow lots of extra I/O to allow different implementations. So for example, we could use a 10 megahertz crystal oscillator as our disciplined source. And then we could also generate 122.88 with a low noise synthesizer chip from that 10 megahertz. Or alternatively, we could keep the 122.88 megahertz oscillator, but instead of locking it to GPS, we could lock it to an external 10 megahertz source, like a local frequency standard. So we'll have the capability to implement the GPS-DO in different ways. And it's also important that the module can be used independently of TangerineSDR. We'll have some sort of an adapter to allow it to mount, for example, on a Raspberry Pi and serve as a standalone system. And of course, the hardware and this firmware are all open source. This is a block diagram of the clock module, and it's probably impossible to read, so I won't try to go through its details. But the key takeaway is that pretty much everything goes through the FPGA, which is this block here. That again allows us the flexibility to reroute signals and to try different implementations. The output is here the 122.88 megahertz oscillator, which drives a 4-way buffer and provides the 4 output signals that are needed by the RF modules. And then we also have other signals that go directly from the FPGA to the output connector, which is this block. So at this point, we have the block diagram finished. We're starting to think about turning it into a schematic and then a board layout. But now that we've tested the GPS units and we know how they work, we're very confident that this design will give us a clock module for the TangerineSDR that not only meets the requirements, but provides in itself a test bed for further experimentation. So thanks much.
Hello, this is an update on the TangerineSDR HF dual channel receiver module, and we'd like to acknowledge support from the National Science Foundation for portions of this project. The purpose of the module is to provide 2 HF channels from about 100 kilohertz to 54 megahertz. It uses the data engine portion of the TangerineSDR to actually process the signals. So this receiver module is, in essence, a dual channel A to D converter, which is connected to the data engine by a double data rate, parallel interface using LVDS or low voltage differential signaling. LVDS is used to minimize noise, and pin count limitations on available A to D converter chips generally require use of DDR to get both channels transferred to the data engine. The receiver's been laid out and the schematic, of course, completed, but nothing's been fabricated or built yet, as we're awaiting the actual data engine and the final pinouts before finalizing the receiver. This is a high-level block diagram of the receiver. There are two antennas, channel 1 and channel 2. Each goes through a relay, and that relay allows selecting either the HF receiver antenna or a broadband noise source, which is about 5 dB excess noise ratio. The noise source allows calibrating the receiver input over its range, and it is isolated when not in use. There's also a pluggable optional filter, which is used, for example, to provide things like AM broadcast station rejection or HF shortwave station rejection. It may also be bypassed if not used, and there's a jumper to bypass it. The two antennas are isolated by transformers, and so those signals can provide common mode rejection without a significant amount of attenuation. There's an optional jumper to bypass those two signals and allow connecting the analog ground independently to the digital ground. The two signals then go into a dual channel ADC driver, and that driver drives the two channels of the 14-bit A to D converter. There's no active components in front of the dual ADC driver, and there are relay switched passive attenuators allowing selection of 0, 10, 20, and 30 dB receive attenuation. This is a layout of the module as we currently have it. There's two SMA connectors on the left side, one for each channel. Those go through the relays, then they go through the filter module, which again is optional, and if not in place, then it can be jumpered around. They go through a filter and transformer and into the dual driver chip in the center, and then to the dual channel A to D converter. On the right side underneath is an MEC connector, and this provides the digital signals that go from this board to the data engine board. This is a diagram of the AM broadcast band passive filter. This is a band stop filter, which is used to get rid of a wide range of AM broadcast frequencies if there are difficulties with strong AM broadcast signals at the particular site. This is a diagram of the filter response, and you can see that the return loss in red is low out of band and is high in band, and that's typical of reflective filters where the filter reflects those signals that are trying to be rejected as a band stop. One thing to note is that the group delay is quite nonlinear in band, and so there's a lot of equivalent time delay in the band rejection part of the filter. Many times one wants to power up remote antennas, and to do that using an isolated receiver would generally be done by using a DC power supply, a bias tee, and then a common mode choke. The common mode choke allows isolating the antenna from ground while still providing DC power to the antenna. The DC power cancels out the two directions in the common mode choke, avoiding saturating the filter. John and Scotty will talk about their portions of the clock module and the data engine respectively.
Hello, I'm Scotty WA2DFI, and I'm going to talk to you today about the TangerineSDR data engine, a quick hardware description, and a hardware status of the system boards. I'd like to thank the support from the National Science Foundation, the generously granted us several grants in support of development of this hardware. Also like to thank ARDC for their generous grant on helping us build, used for helping us build additional hardware prototypes beyond the ones supported by the NSF. So here's a block diagram of the data engine. It's modular construction. The first module I'll cover are the RF modules. They're used for getting the data from the antenna into our data engine. It consists of 240-pin connectors. Each connector will support up to 1.5 gigabytes per second of data transmission over 96 differential pairs. The two connectors are arranged so that you can use them in tandem to get 3 gigabytes per second over 192 differential pairs. Next, we have the clock module, which I believe John Ackerman has already talked to you about, but it's not required for a low-cost system. However, for higher performance, if you need a high stability VCXO or an oven controlled oscillator or a GPS disciplined oscillator, that will be a socket that you can plug the clock module into on the data engine to get the higher performance clocks. The DE is based upon a Max 10 from Intel. We're going to use the largest Max 10 50,000 LEs and the highest speed grade, the Dash 6, and industrial temperature range. So we're going to use basically the fastest and best Max 10 part we can get. The Max 10 will be used for pre-processing the IQ data samples and packetization into Ethernet packets. We'll have a micro SD card for expansion or upgrades. And also, as far as additional memory, non-pluggable memory, we are going to have a bank of DDR3 DRAM, 4 gigabits worth of it, and we're going to use that to run microprocessor, softcore microprocessor code inside the FPGA. And as far as flash goes, we're going to have a 512 megabit QSPI flash and a 512 K-bit serial flash. So we'll be able to store additional program data to be loaded into the RAM and executed that way. We execute out of RAM. The interfaces here on the bottom, we're going to have a USB 2 host used to plug in DVB dongles, a USB 3 device, which is a 5 gigabit per second full duplex device port. That'll be used to transport IQ data to a host PC. We're also going to have gigabit Ethernet, and we're going to have a switch on board, which allows us to connect directly to a local network as well as a local single board computer at the same time. Up here on the right, we're going to have an expansion header similar to the Raspberry Pi. It's actually compatible with Raspberry Pi hat boards, and we have an additional connector with some high-speed differential I/O on it, which will enable the Leaf module, which is our Raspberry Pi hat name. The Leaf module will be a little more flexible than the Raspberry Pi hat because we'll have some high-speed I/O as well as the lower-speed serial I/O. This is a layout of the data engine module. You can see the connectors in the upper left for the standard Raspberry Pi, the Leaf connector, the expansion connector, and the clock module on the lower left. And I'll show you here kind of assembly of everything put together. The RF modules are on the back side, and you can see in blue here, and they extend up beyond the data engine on the back side. On the top side, we have the clock module in the lower right, and the Raspberry Pi hat or Leaf board in the upper left. So it ends up becoming a 3-board stack with the RF modules on the bottom, the data engine in the middle, and the Leaf and the clock module on the top. So when can you get one? This is the scheduled dates, scheduled well-planned dates. The receiver module is all done and ready for production. We're just waiting on the placement of the data engine to make sure everything fits together so that we don't have any surprises with mechanical interference or anything like that. So scheduled for December 2020. The clock module's in process right now, and the first one out is going to be using the ZF9T. John's already talked about that. We're estimating February of 21 for that. The data engine, January of 2021 for the data engine. And the magnetometer, Raspberry Pi hat, looks to be October next month, October of 2020. And Dave Witten is going to talk to you a little bit more about that. Thank you for your time, and check out TangerineSDR.com for any future updates. Okay, it looks like we've got John and Tom and myself here to answer any questions.
And Scotty, I fear that as a moderator, you may have to read the questions from Q&A and distribute them and answer them unless Nathaniel's willing to do that.
Oh, well, Nathaniel and I can jump in and help.
Yeah,
Well, at least I'm not chewing gum, so I can read at the same time.
Oh, let's see, where to
Go ahead.
begin? Well, why don't we start with some easy questions, Bill, or easy questions, Scotty. Bill Engelke asks, can I use Leo Bodner GPSDO before the TAPR one is ready?
And I guess I should answer that. Probably not, because the clock module is going to provide, well, actually, yeah, probably not. We need 4 outputs of 122.88 megahertz, and the Bodner can probably provide that frequency, but you'd need to have the fan out to be able to drive 4 differential lines. So you'd need a hardware widget at a minimum to be able to do it.
And why, I think this is Scotty, why did you design the RF connectors 90 degrees off from the IO connectors? Doesn't that complicate packaging for cases?
Yes, it does, but it eliminates the impossible packaging for the electronics, because if you rotate the RF boards 90 degrees, then it puts the FPGA underneath the leaf board, and that's not really a doable thing. So the FPGA is going to be in the lower left corner of that diagram I showed you, which is open, because it has to, first of all, it has to be open for the height, and then we're most likely going to end up with a heat sink glued onto the top of it because it's a nice heat generator. So yeah, it does complicate it a little bit. However, we did restrain it to only 2 sides instead of 3 or 4 sides, so that might help make it possible anyway. Hope that answers the question.
And Graham asks, where can you get a user-friendly F9T receiver?
I don't really know. The last time I checked, no one was making, no third party was making an evaluation board for the F9T. So you're kind of stuck. I shouldn't really mention this, but as a side project, I've been doing a carrier board, basically evaluation module that you can put both, or either an F9P or an F9T on and get it all the IO. And that board is finished and working. I'm happy to make open source design, anybody who wants to copy it. It does require a toaster oven for assembly because there are a bunch of pins, ground pads on the bottom of the F9 module that you cannot hand solder. But I can certainly provide the files for that if anybody wants to try to build one.
And Richard Stanley says to John, did you try the U-Blox dev board for the F9P? How's the SMA connector compared to the one on SparkFun?
No, I didn't, because I only had one board. Yeah, the U.FL connector is kind of a pain to deal with. However, SparkFun now has a version of that board with an SMA on it. So you can, same price, you can request it with either type of connector. So they've made that a little bit easier. That came out after I bought mine.
And then Scotty, do you anticipate the Tangerine stack requiring anything besides passive cooling?
Unfortunately, the answer is most likely yes. We may be able to design the case with some conductive pads on it to conduct the heat away. That the big heat generators are going to be the A to Ds on the receiver boards, and the FPGA itself. And I think the idea is by keeping it in the stack, we put a heatsink on the FPGA, and the A to Ds are actually mounted on the back, on the receiver boards are on the back, and their components are on the back side. So basically the heat generating components are both on the outsides of the tree board stack. if we put small glue-on heat sinks on those, we may be able to use a very small lateral fan to blow air through the stack of 3 boards. It takes very little air to cool the FPGA. I'm not sure. They think the ADCs are probably about the same heat load as the FPGA. So the short answer is probably not. You may be able to operate it that way on your bench as a test for testing, but it's likely to either require a fan or some kind of clever case mechanism to conduct the heat away.
Sounds good. Let's see. And so back to John, for timing, is the only advantage of the F9T over the F9P the lower price?
It does offer 2 time pulse outputs that can be independently programmed. So that could be useful for some other applications. And it also has 2 ability to clock external inputs, which it has 2 of those as well. Unfortunately, in my testing, I discovered there seems to be a problem with using that external input for what we would want to do. But the main reason is it's cheaper. Having the extra time pulse signal could be useful later, but it's not something that we're currently making use of.
And Scotty, Rich Stanley asks, can you share the link if public yet for the code for the Altera FPGA? And then he says, pretty sure it's Altera.
Yes, it's Altera, which is now Intel. So it's because Intel bought Altera. So it's an Intel Max 10 M50 FPGA, and currently I don't have a public link yet. I'm still finalizing the schematic design for the data engine, and at the same time I'm designing the initial framework for the FPGA, because as you FPGA designers know, that it's the Quartus design tool that tells you whether you have made any errors in your pin connections. So before you commit your board design to actual copper, you had better build an FPGA image with all the pin connections and make sure that they all work. So that is in process right now. When we get a FPGA design that actually does something useful, like maybe even test code, self-test code, we'll be putting those links up, because this is all going to be open source. So it'll all be available once we get something useful.
That sounds really good, Scotty. Thank you. Let's see, are there any extra questions? Any more questions out there? John, I have a question. I know that the other John, NAOBJ, was wondering if we could do anything cheaper than the Leo Bodner GPSDO for the low cost station, but you said that you're using the dual frequency, which is more expensive. But if we went to a single frequency chip for the low cost station, do you think that could help that out?
It's an interesting question. It would require a board redesign, because the footprint for the dual frequency module is different than the single frequency. And it would probably not offer quite as much performance unless we went to a more expensive crystal oscillator. But conceivably it could be done, but it would be a different hardware module than this one.
Would it be, when you say it would be worse performance, would it be performance on par with using the Leo Bodner? Or would it be at least, would it be good enough? Do you think it would be good enough performance to meet the requirements of a low-cost personal space weather station?
It probably could, but there are a number of differences. So first, I don't think the frequency that John is going to require is a VHF clock frequency. I'm assuming it's a 10 megahertz input or something like that. Mm-hmm. So we're set up now to make the VHF signal. You could replace that with a lower frequency oscillator. And then it just comes into an issue of the cost of the oscillator versus the performance. But you know, everything's a balancing act in how you take cost versus performance versus complexity of the loop design.
Yeah.
But
maybe we can talk about that with John NAOBJ offline or later. Because we're coming up to the next presentation now.
Yeah, and I'd like to talk to Tom also about receiver performance, maybe during the break.